Hello AP Chemistry and welcome to 16.6. Probably this is just going to be part 1 as we introduce the concept of weak acids, right? So now everything up to this point should be relatively straightforward, right? Now the only reason that weak acids gets a tiny smidge harder, right, is because we're going to go ahead and take everything we know about acids and bases and pH and we're going to layer in equilibrium, right? Because weak acids and weak bases are, ding, 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 right? Weak acids and weak bases are weak electrolytes, right? Meaning they only dissociate some, right? They don't dissociate completely, they dissociate some. And if they only dissociate some, then that means the math has to become a little bit more thoughtful, right? But really, all we're going to do is take those exact same principles we learned in the previous chapter, and that's going to determine our weak acid math, and then we'll just do normal pH calculations on top of it, right? So it looks hard, but it's not. It's not harder than the last unit, okay? All right. So first, for starters, let's talk about, let's say we had some HF plus H2O, and we were deciding what to write on the product side for the hydrolysis, right? So first of all, we would say to ourselves, well, is HF a weak acid or a strong acid? And you would say, ding, 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 right? It is the only hydrohalic acid that is a weak acid, and we would then say F minus plus H3O plus as our products with the equilibrium arrows, right? Now, thinking about how to write an equilibrium expression, because again, anything that doesn't go completely forward and can be expressed by the fact that it goes backwards and forwards, it's going to have a K expression, which we're going to denote as Ka, right? Where that A is what tells us this is the K for an acid, right? Or the acid dissociation constant, right? And we're going to have F minus up here and H3O plus up here. And down here we will have our reactant, which is HF, right? We will exclude water because, correct, pure substances, pure liquids and pure solids are excluded from our K expressions. So now we have that, right? And that is the acid dissociation expression, right? So same thing like last chapter, if you're just asked to write the Ka expression, that's all it's asking for, right? So we have our reaction and we have our K expression, and then obviously those concentrations, right, or in terms of like how much it dissociates, is governed by, right, whatever my Ka value is, right? Does that make sense? Okay, and then so looking at this diagram from your guys' book, right, this is just showing you the same thing at the particle level, right? In that if we have strong acid HA, if we look at our microscopic picture, again, there are no molecules of HA present, yes? All of it has reacted with the water, right, or undergone hydrolysis with the water. Whereas for a weak acid, HA, right, we actually still have a boatload of HA still floating around, and in this particular instance, only one molecule dissociated or underwent hydrolysis with the waters. Yes? Does it make sense? All right. Now, looking at acids, and this is something we kind of talked about previously, right, where one of our big sources of acids are going to be these COOH, carboxylic acid groups, okay? In addition, we have ones that we already kind of know about, right, like hypochlorous acid, chlorous acid, nitrous acid, right? Note there, we don't often look at the structures, right, but note that that hydrogen is always stuck to the oxygen part, yes, as in chlorous acid, nitrous acid, hypochlorous acid, all of those are oxyacids, going back to naming from sophomore year, which means at the root, right, there is that polyatomic ion, and then there's a hydrogen stuck to that polyatomic ion, right? So we should always remember polyatomic ion that has a hydrogen attached to it at an oxygen, yes? Polyatomic ion that has a hydrogen stuck to it at an oxygen, okay? If it's an oxyacid. Obviously for the other ones, right, like cyanide, we learned cyanide last year also, right? In this case, it's stuck to the carbon, right? All right. Fantastic. And then, again, there's no expectation you could draw all of these, or just know all these. Like if I said benzoic acid, there's no expectation you know benzoic acid, right? But yeah. All right, next up, let's do a tiny bit of math, employing all the things that we know. So niacin, we have a 0.02 molar solution of niacin, and it has a pH of this, and we would like to figure out the acid dissociation constant. So what seems like a great place to start? Ding, 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 write the reaction, right? So we have our niacin, which, you know what, we are just going to symbolize as HA plus H2O gives us H3O plus plus A minus, okay? Now, let's see what we know, right? We know that we have 0.02 molar this, right? And what else do I know? Right, I know that I have a pH is equal to 3.26, which means that, correct, I also know my H3O plus concentration, yes? So we'll go ahead and solve for our H3O plus concentration. All right, so we have our H3O plus concentration, which is also our, correct, that's also our A minus concentration, right? And this goes back to like what we talked about when we did KSP, right? If everything comes from the same dissociation process, then that concentration reflects all the species, yes? So we know that that's what happens down here, right? So, oh my gosh, look at this, right? This is what we've done before. This is 5.5, E negative 4, 5.5, E negative 4, which then makes X that, right? So then 5.5, E negative 4, right? And then we would just solve, right? So when we are solving, we should have written our K expression, right? So Ka is equal to H3O plus times A minus over HA, right? Which now, Ka is equal to 5.5 E negative 4 squared over 0.02 minus 5.5 E negative 4. Yes, does that make sense? And that's going to give us our Ka value. All right. Now, going back to your book and stuff that we've talked about previously in chapter 15, right? Depending on how small that minus X component is, you can neglect it, right? So for example, when we do multiple choices, and we do multiple choice practice later, you'll see that pretty much we're just going to always neglect minus X, right? Because then if we have to incorporate that minus X, it becomes math that we can't quickly do by hand, right? Or in our head. But if you guys have your calculator on you, there's no reason to have to neglect X because everything is so fast and easy with your calculators at this point, right? Does that make sense? So anyway, just a note. All right, and then so the follow-up question says we have, oh my gosh, that same solution with that same pH, and we'd like to know the percent ionization, which is just going to be the amount that ionizes, right, over the original concentration. Yes, the amount that ionizes over the original concentration, right? So if we're looking at that, amount that ionizes over the original concentration is going to give us our percent ionization, right? Because percent always means the same thing. All right, next up. The Ka for niacin is that, what is the pH of a 0.01 molar solution of niacin? So, same thing, right? We would start by writing our reaction, right? And then we would have this plus that. We would write our Ka expression, which is H3O plus times A minus over HA is equal to 1.5 times 10 to the negative 5. And then we'd fill in our concentrations, right? And here, whether or not you need to write out a full rice table kind of just depends on where you are in terms of your comfort level, right? And that's going to be different for everybody, and so I can't tell you what that is for you, right? For example, right, we could start by saying 0.01 molar, right? So 0.01 molar, right? And 0, 0, right? And then obviously this would be minus X, and this would be plus X, right? And then now we could put that in there, right? And that would be okay, right? So then we could just plug in those values, right? Which say that we have X squared over 0.01 minus X is equal to 1.0 times 10 to the negative 5. And then we would solve for X, right? And then once we had X, we could then put it into the pH expression, right? Does that make sense? So here it's just about keeping organized. Whether or not, again, you need to do this whole rice table sort of depends on where you are and whether or not you can visualize that in your head. And if you cannot, please just go ahead and write it out, right? It doesn't take very long at this point because you guys are so well versed in it. And if it's going to help you solve it correctly, then it's a good thing to do. All right. Thank you for listening. Be good, and I will see you soon. Stay tuned for weak acids 16.6 part 2 coming up.